So students, in the last lecture we have seen about improper integrals. There we have seen about first kind of improper integral and second kind of improper integral. We have also seen some of the examples based on first kind of improper integral. That means when the limits are infinity or minus infinity. Okay? So now let us see more examples. Let us see one example. Check the convergence of integration 0 to infinity x raised to 10 into 1 plus x raised to 5 divided by 1 plus x whole raised to 27 dx. So, see, the limit is infinity, so it is an improper integral. Okay? And one more thing here. It is improper integral that we have identified, but now to solve. Let us first focus on the given function. That means we call this as an integrand. Okay? And you can see that the integrand is very difficult to integrate directly. We cannot integrate it directly. So to do this, we will have to simplify the given integral by using a comparison test. So here we will start the solution by writing this in this way. We have f of x equal to x raised to 10 into 1 plus x raised to 5 divided by 1 plus x whole raised to 27. And as per the comparison test, we will find out its equivalent function. In numerator, and this is one more thing here. I told you that it is under this condition as x tends to infinity. That means wherever x is very large, then we will find out its equivalent function. So we can see that when x is very large, there is no effect of 1. So the highest power of x is here 15. So it is equivalent to x raised to 15. It is again equivalent to x raised to 27. So this is what? 1 upon x raised to 12. Okay? So we will consider this as gx directly. And now we will check I2 equal to integration. Before of that, just I would tell you that we have seen in comparison test and we want to check its convergence. And for this convergence, we have seen one p integral. Just like p integral is 1 upon x raised to p dx for a to infinity, and there we have seen that a greater than 0. A must be greater than 0. And this is convergent if p greater than 1, and it is divergent if p less than or equal to 1. But here we can see that the lower limit is 0. So we cannot apply the comparison test directly, because here we want to use p integral, and that's why in this p integral a is greater than 0. So we will have to write down first. We will the given integration we will denote by I1, and we will split this into two parts. First we will write down 0 to 1 x raised to 10 1 plus x raised to 5 and divided by 1 plus x whole raised to 27 dx plus 1 to infinity x raised to 10 into 1 plus x raised to 5 divided by 1 plus x whole raised to 27 dx. Okay? So in the last lecture also we have seen one example of this kind, to how to split the integral. Here we have written 0 to 1 and 1 to infinity. You can also write 0 to 2, 2 to infinity, but we will use the simple numbers over here, so as we can understand this very easily. Okay. So now see, this integral has the limit 0 to 1. Okay. So it is not infinity. So we will focus on the integration, whether it is discontinuous, that means if it is of the second kind or not. If we try to put the values between 0 and 1, including 0 and 1 in this function, then it will not become infinity. That means the function, complete function is continuous between 0 and 1. So this integration is already convergent. This integration is already convergent. So actually we will write down this as, suppose I will write down this as I1, okay, no problem, I1, and this I will write down as integration I1 plus I2. So here this is our I1. I1 is convergent, because here we don't want to find the value, we want to see the convergent only, whether it is convergent or divergent. Convergent as x raised to 10 into 1 plus x raised to 5 divided by 1 plus x whole raised to 27 is convergent in the closed interval 0 and 1. Okay. Sorry, as it is continuous, continuous, as it is continuous in 0, 1. So it is already convergent. So we have to check the convergence of this integration only. And for this we will use this comparison test now, because it is 1, so 1 is greater than 0. So now we can apply. Okay. So now for I2, what will we do? For I2, this you will have to write, due to space I have rubbed out it. So now I2 equal to integration 1 to infinity, because we are checking this, so same limits we will use, gx dx equal to integration 1 to infinity 1 upon x raised to 12 dx. Okay. So if we compare it with this p integral, so p equal to 12, p equal to 12, and 12 is greater than 1, so it is convergent p integral, okay, by our p integral theorem. So it is convergent, and therefore we say that this I2 is also convergent. Okay, I2 is also convergent. So we know that now both integrals are convergent, and therefore we say that our integral I1 is convergent, because both integrals are convergent. So I1 is this I1. That means the example is also convergent. So here you must note that due to the lower limit is 0, and as we are not integrating it directly, and we want to apply here comparison test. Okay, we want to apply comparison test, and that's why here we need the number greater than 0 instead of 0, and to do this we have split the integral into two parts, and then we have used comparison test, and this we applied on the second integral only, because this is convergent directly as it is continuous function. Okay, so you note down this problem, and after the end of this lecture I will give you sufficient time to practice yourself all the examples whichever I have discussed on this board. Okay, so now let us see one theorem which is also very much useful in solving the other examples. That means if integration of a to infinity, see here the limit, lower limit is a, modulus fx dx is convergent, then integration a to infinity f of x dx is also convergent, and this is known as absolute convergent. Absolutely. Okay, absolutely convergent. So this theorem is applicable when here the function is not integrable, and also it is not possible for us sometimes to apply comparison test. Then we can apply this theorem. That means we can find out its absolute value, that means modulus of fx, and then we can check out its convergence. If it is convergent, we can also say that it is also convergent. So let us see example. It will be clear to you from the example. We will check the convergence of integration 5 to infinity cos x upon 2x square plus 1 dx. So now see here in this problem we can see that the integration of this is very difficult and not possible easily. So we may think of comparison test. But to do this comparison test, we have to find out the approximate function of comparison test. But approximate function of comparison test is also very difficult to obtain in this case, because we are not given directly the rational function. That means numerator and denominator both are algebraic functions. Here in numerator we are given trigonometric function, that means cos x. So we do the different thing. So in the solution we will assume let f of x equal to cos of x upon 2x square plus 1. Okay, f of x equal to cos of x upon 2x square plus 1. And therefore what will we do? We will find out its modulus. We may try it for its absolute value. That means modulus cos x upon 2x square plus 1. But you know that modulus cos x is always less than or equal to 1. So this is less than or equal to 1, modulus cos x. And 2x square plus 1, we cannot write, we will avoid to write modulus sign, because 2x square plus 1 is itself is positive. Because it is x square, 2 is also positive, 1 is also positive. So this is less than or equal to 1. Modulus cos x is always less than or equal to 1. Similarly, we can also say that modulus sin x is also less than or equal to 1. Now we will find out its equivalent function. Now we will go for comparison test. So this is equivalent to 2x there. Okay? As x tends to infinity. As x tends to infinity. And you must write down this in this case. So this is nothing but 1/2 into gx, because we are writing this as c into gx, as we discussed in the last lecture. And therefore we have integration gx dx, and the limits of integration we will use the same 5 to infinity equal to 5 to infinity. This is gx is 1 upon x square. It is 1 upon x square dx, and is convergent p integral, because p equal to p integral. P equal to 2 and p is greater than 1. And therefore, see now, integration gx is convergent, and therefore by comparison test, modulus fx dx, because we have obtained the equivalency of this function, modulus fx is convergent. Okay, and it is convergent. So by using this theorem, we can say that integration of 5 to infinity fx dx is also convergent. Okay, is also convergent. So this is the solution of this example, and you might have observed it that the problem is very simple, nothing is difficult here. Okay, Did you get it? Okay, you note down it, and then at the end of the lecture you may try to solve it yourself. Let us see more examples now. Example, evaluate integration 3 to infinity dx upon x minus 2 whole square. Okay, so here this example is very simple because this is improper integral. So we have I equal to, see here, 3 to infinity. So we will make the use of limit. Here we will write down t tends to infinity dx upon x minus 2 whole square. So this equal to limit t tends to infinity. The integration of this one is minus 1 upon x minus 2, because the integration of 1 upon x square is minus 1 upon x. Okay, so therefore this is equal to limit, we put x equal to t, so minus 1 upon t minus 2, lower limit and minus sign will come plus 1 upon 3 minus 2, 3 minus 2 means 1. So now we put t tends to infinity the limit. Here if we put infinity, 1 upon infinity equal to 0. So plus 1, 0 plus 1 is 1. So its answer is 1. Okay, so this problem is also very simple. Now let us see another example. Another example is integration 4 to infinity sin square x dx, sin square x dx upon root x into x minus 1 divergent. The question is that is it is divergent? Question mark is divergent, that means it may be convergent also, but we will have to check this one properly. Here we can see that the function sin square, it is improper integral, first criteria. Second thing is that this function is not integrable directly. Okay, and in numerator there is a sin square x. So here we will try to use the absolute convergent theorem that we have seen in the last example. Okay, so we will take, let f of x equal to sin square x upon root x into x minus 1, and therefore we will take modulus x, f of x. So modulus of f of x is modulus sin square x divided by root x into x minus 1. And as we discussed that modulus sin x is always less than or equal to 1. So this is less than or equal to 1. Now see, here root x we can write it as it is, because x belongs to 4 to infinity. X is greater than 4. X greater than or equal to 4. So root of x is always positive. So no need to use modulus sign. Here again x minus 1. In x minus 1 also no need to use modulus sign, because as x greater than or equal to 4, x minus 1 is also positive. So we will find out its equivalent function now. We go for comparison test. That means it is root x into x. That means this is 1 upon x raised to 1 half into 1, so 3 by 2, and this is what as x tends to infinity. You must write down this as x tends to infinity. Okay, this is very much important, and therefore this we will assume as gx. Therefore we have integration of gx dx, and the limits are same. 4 to infinity is equal to 4 to infinity is 1 upon x raised to 3 by 2. Here p equal to 3 by 2 and it is greater than 1. So is convergent p equal to 3 by 2 integral. Okay, it is greater than 1. And it is convergent, and therefore integration 4 to infinity modulus fx, because we have compared this modulus fx dx is also convergent. Okay, and as it is convergent, by absolute convergent test we can say that integration of 4 to infinity fx dx, here we have assumed this equal to f of x, so no need to write down this again and again. So to avoid this lengthy writings, we will use fx dx is convergent. So it is convergent, so it is not divergent. That means not divergent. It is convergent, that means not divergent. Okay. So if this kind of examples are asked in examination, then you can solve these examples in this way. So here you note down this example. Now let us see one more example. Find the area lying to the right of, find the area lying to the right of x equal to 3 and between the curve y equal to 1 upon x minus 1, y equal to 1 upon x square minus 1 and x axis. Okay, so actually it is the case of finding area, and problems of finding area under the curve you have seen in 12th standard. But however, here I will explain you in short way. That means if it is x-axis, if it is y-axis, if it is the graph of function of fx, okay, and if we are considering the limits from a to b, then to find out the area below the curve and above positive x-axis, below the curve fx, that means below the curve function of graph of f of x, and above x-axis and between x equal to a, because this is nothing but, this line is nothing but x equal to a, and this line is nothing but x equal to b. So to find out this area we have the formula that simply integrate the function fx with respect to dx between the limits a to b. So this we can find out area, a for area. So here in this solution we can use same kind of situation. So find the area lying to the right of x equal to 3. Here no need to draw the graph. You can understand directly, because to the right of x equal to 3, that means on this side we want to find out the graph and the curve. Actually the graph, drawing of this graph is a lengthy process. So we will not discuss it, how to trace out this curve, which kind of this curve is there. Okay. So we will simply understand as suppose it is of this kind and x-axis, okay, and to the right of x equal to 3 and above x-axis. So the boundaries are there. It is x-axis, it is this curve, it is on right hand side. That means the area extends up to infinitely. Actually, we don't know which kind of this curve is there. Actually, by looking this, it is it may be of this kind of curve. It may be this kind of curve. Okay. Actually, there are also procedures to trace out the curve, but here we will not see at this stage because there are so many rules and regulations to follow to trace out the curve. But we will understand that we want to find out the area to the right hand side. But here we show that there is no boundary on right hand side. There is no boundary on right hand side. So required area A equal to integration. See, lower limit is 3 and there is no boundary on right hand side. That means the value of x extends to infinity. It is up to infinity. And what is the curve above? Fx. Fx is y equal to fx here. Fx is nothing but here y. So it is 1 upon x square minus 1 dx. Okay. So this is the area. So the problem is very simple. So you don't get hesitate by looking at the statement of the problem. Once if you write down this, then you are at the right stage now, and it is very easy to solve this problem. Okay. Now you can see that this is an improper integral. So actually it is the application of improper integration, and in this sometimes the examples of this kind can be asked. So here we will make the use of limit, and here 3 to t tends to infinity 1 upon x square minus 1 dx. So you must be knowing the formula for 1 upon x square minus a square dx. Okay. The formula for this is 1/2 log of x minus 1 upon x plus 1, x minus a upon x plus a, and 3 to t. Okay. So this equal to limit t tends to infinity 1/2 log of t minus 1 upon t plus 1 t plus 1 minus 1/2 log of 3 minus 1, that is 2 by 4. 3 plus 1 4, 2 by 4. So now see, we will find out the limit as t tends to infinity. So what will we do? Here there is no t inside this, so this value will remain as it is. But to solve this limit, here if you put directly the value t equal infinity, then it will become complicated situation, and we cannot understand this properly. So to do this, just we will try to solve this, put it into simple form. We will divide the numerator and denominator by t. So if we divide numerator by t, we will get 1 minus 1 upon t, and if we divide denominator by 1 upon t, then this will get 1 plus 1 upon t, and the minus, this is nothing but log of 1/2 because it is already the value, there is no t inside it. So now if we put t tends to infinity, you know that 1 upon infinity is 0, so it is 1 now. Here again 1 upon t is infinity, so it is 1. So 1 upon 1 is 1, but log of 1 is 0. Log of 1 is 0. So its answer is minus 1/2 log of 1/2. So this is the answer, and you note down this the value. Okay, you note down this one. Sorry, here 2 plus 1 is 3. 2 by 3. So this is 2 by 3. 3. Actually, see, 3 plus 1, 4. 1/2. Yes. 2, 3 limits we were putting. No. 3, yes. 3 minus 1, 2, and 3 plus 1, 4. Okay, correct. 1/2, and it is 1/2. Okay. So this is the answer. You can see and you can observe it very clearly. So you note down this problem. Now let us see one more example. Check the convergence of integration 0 to infinity 1 upon 1 plus x square into 1 plus tan inverse x dx. So here we can see the solution is very simple, but by looking to the example you may be thinking that this is very difficult. So first of all, as I told you in last lecture, that first of all you see whether this is integrable directly or not. If its integration is simple, then you don't have to worry. You can do it directly without using comparison test or without using absolute convergence test. Okay. So now here I know that the integration is very simple, because here if we will first of all we will have to write out this into limit 0 to t tends to infinity, and if I will write down this 1 plus x square in numerator, okay, 1 plus x square in numerator, and here 1 plus tan inverse x dx, because we know that the derivative of tan inverse x, we know that it is 1 upon 1 plus x square. So derivative of tan inverse x is already in numerator, so its integration is very simple. I told you last time that if g dash x is there and divided by gx is there, the derivative of gx is there, then we can have its integration is log of gx. Okay. So t tends to infinity, its integration is nothing but log of 1 plus tan inverse x and 0 to t. Simple. At first look, we can observe that it is very difficult. But after understanding, we can see it is very easy. So limit t tends to infinity, log of 1 plus tan inverse t minus log of 1 plus tan inverse 0, but tan inverse 0 is 0. So if we put t tends to infinity, here tan inverse infinity is pi by 2. Pi by 2, and log of 1 is 0. So it is the answer. It is the answer. So you must have seen that this is the answer of this problem. Okay. Now, so you must have noted down this, and I told you that during the remaining time of this lecture, you will have to solve all these examples whichever I have solved on the board. Now, the second kind of improper integration. Second type of improper integration. Second kind of improper integration. Already I discussed to you in the first lecture, but here we will see examples and techniques based on second kind. So we will see more details in the second lecture, but now here I will explain you some of the things. Okay, we know that the integration a to b, here the limits are not infinity. F of x dx is said to be second kind of improper integral if f of x is not continuous, that means discontinuous within a B interval. Okay, closed interval A to B. If it is not discontinuous. So here again we will see, as we have seen three types in first kind, here again we will see three kinds in second kind. Okay, so first of all we assume that suppose f of x tends to plus or minus infinity at x equal to b, only one point, that means only at x equal to b. Suppose if it is tends to plus or minus infinity at x equal to b, that means we say that it is an improper integral of second kind. So therefore in this case we can solve this problem in this way. That means if it is real line, if it is the point A, if it is the point B, we say that it is discontinuous at the point B, but everywhere it is continuous. Starting from A to near B, it is continuous. So we will make the different idea here. We will again here use limit, but not just kind of infinity. Here, what will we do? Here it is continuous from starting from A to the point near to B, near to B. So only we are falling into a problem only due to the point B. So just we will consider a point on left side near to B, near to B. Okay, that means at some distance epsilon, that means B minus epsilon. So we suppose that the distance between these 2 points is say epsilon. Nearest, here we will consider epsilon tends to 0, that means B minus epsilon is the point very near to B, and we are considering on left side of B, left side of B, left side of B. So we have written here B minus epsilon. So we will write down here B minus epsilon. So then there is no problem on this integration, because now f of x is convergent, f of x is continuous or bounded starting from A to B minus epsilon. And here we will consider epsilon tends to 0, because the epsilon is very very small, because we are considering the point very very near to B, very very near to B. So we will adopt this idea where it is discontinuous, that means fx tends to plus or minus infinity at x equal to b. Second type is that suppose f of x tends to plus or minus infinity at x equal to a. That means here, if it is the point A, if it is the point B, then we say that it is discontinuous continuous at x equal to a. Otherwise, it is continuous at every point starting from near the point near to A to B. So we will consider the point near to A on right hand side, because we cannot consider this point, because we have to work out within A and B only. So if we consider this distance as epsilon, so this point will become A plus epsilon, because on right hand side of A. So therefore, this integration A to B f of x dx can be written as limit. Here we will write down A plus epsilon, B remain as it is, f of x dx, and here it is epsilon tends to 0. Okay? Have you understood this thing? So in this way we can do it. Now suppose, okay, the third type we will see in the second lecture, next lecture. Okay, till now just I have given you the idea of the second kind improper integrals. Okay, the more things we will see in the next lecture. Till then you can solve the examples yourself. Thank you.